This is section 6.2. We're comparing two proportions with a simulation-based approach. And we're going to start by going over our dolphin study that we did in our last section. So researchers randomly assigned 30 subjects to swim with dolphins or not and evaluate if their depression improved. We want to determine whether the group that swam with dolphins was significantly more likely to show substantial improvement than the group that swam with dolphins. Okay. Or just like we've been doing for this entire course, we're trying to say, okay, there's a difference, but is that difference statistically significant? Would it have happened just by chance? So here's our data again. And we found the proportion of people in the dolphin group that improved is 0.667. So that is my sample proportion for the dolphins. And the proportion of people in the control group that improved is 3 out of 15 equals 0.2, or that would be my sample proportion for the control group. Now we said there's different ways we can compare these, and we're mostly going to work with the difference. So if we want to find the observed difference in the conditional proportions, that's what we're going to call our sample statistic, is what we're actually going to be doing all of our simulations on. So it's just the difference in the sample proportions. And so you just do 0.667 minus 0.2. So that gives me 0.467. So that was the difference that I saw in my sample proportions. Well, what can explain the differences in these proportions? There are two possibilities. The first one, so number one, is that dolphin therapy works. And number two is that dolphin therapy does not work. So if you look back up at our table, if you look at the improvement row, there were 13 people total that improved and 17 that did not improve. So there were a total of 13 people that improved. It's possible that they were just going to improve based on other factors in their life, regardless of which group they're in. Maybe they were people that do meditation every day, or maybe they were on a better diet, maybe they had better family connections, like whatever it was, maybe they were just going to improve, and it had nothing to do with the dolphins. Okay. So maybe it's just a coincidence that when we randomly assign people to groups, we happen to put the 10 people that were going to improve in the dolphin group and 3 people that would improve in the control group. Okay, and that's certainly possible, but is it probable? Now, in our textbook, it'll say there's only 2 possibilities, and on the homework, it'll ask you and say there's only 2 possibilities, okay? Now, theoretically, there's always a possibility of something being wrong in the study design, like broken equipment. Remember that Buzz and Doris one where they had broken equipment, so it didn't seem to work? Or maybe people figure out which group they're in, so they think they're getting a better treatment, so the placebo effect comes into place. Or maybe crew members are smuggling depression medication in the dolphin group, okay? Who knows what it is? There are oftentimes in studies that something is breaking the study. And if something's breaking the study, then that's kind of a third possibility. But for this class, we're assuming that it's a well-designed study, nothing broke it, and then we only have 2 options left, which is either the dolphin therapy works or dolphin therapy didn't work. Okay? And if dolphin therapy didn't work, then it's truly just the random chance of who got put in what group that is giving us the results. So let's think about this. If dolphin therapy does not work, and so 13 out of 30 people were going to improve regardless of whether they swam with dolphins or not, how many people would you expect to improve in each treatment group? Okay. Well, if dolphins have nothing to do with it, you would expect about half the people in each group. So if you're expecting about half of the improving people to be in each group, that would be, so like 6 or 7 people to improve in each group, since you can't actually have half a person. But that's not what we saw. We actually had a 10-to-3 split. Let's look back at the table again. There were 10 people that improved in the dolphin group, 3 people that improved in the control group. But we're saying if dolphins had no effect, we'd expect about 6 or 7 people to improve in each group. Okay? So how unlikely is it for us to get a 10-to-3 split just by random chance, just by the chance of who we put in each group? So in this situation, all the randomness in the study is just the actual random assigning process with how we randomly put the people into the groups. So to answer this, we're going to replicate the random assignment process over and over again, but in a situation where we're saying that dolphin therapy doesn't do anything. Okay, so we're saying it's just as effective as nature therapy. Any difference is just random chance. To do this, what we do is we fix the response outcome to have 13 improvers and 17 non-improvers, and we kind of shuffle everyone together and deal out 15 people to be in the dolphin group and 15 people to be in the control group. Now, how do you actually do this, hypothetically? The easiest way isn't with cards or dice like we did before. It's actually, dice or coins. It's actually use playing cards or like index cards, just some kind of cards. Okay. So you'd gather 30 cards, that's how many people we had, and you'd have 13 of them be the improvers. So 13 improvers, and then 17 as the non-improvers. Now you could write on them, you could color them different colors. Okay, you shuffle the cards really well, and you randomly deal out 15 to be in the dolphin therapy group, 15 to be in the control group. And then you construct a table like we had up above that shows your data, like how many people improved in each group. And then any differences that you see in the two groups have to be just due to the random assignment process. It can't be blamed on anything else. And then you find the simulate statistic, which we said is the difference in the proportions. That's the statistic that we're interested in after each shuffle. So we're going to use the ISI applet. Let's pull that up. So to use this applet, I put in the data just like we did before. It's a 2x2 table. I put dolphin, control, improve, not improve. Remember, no spaces in your headings or it won't work for you. You have to actually click use table. There's been lots of times I didn't actually click it and I wondered why it didn't seem to be right. You can see the proportions in each group that improved. I can click show table. And now it will tell me my conditional proportions and it will tell me my observed difference in proportions because that's the statistic that I'm using. Then I click show shuffle options. I'm going to do just one shuffle. Okay. You'll notice these people, okay, like these were the 10 people that were succeeded, that improved in the dolphin group. These are the 3 people that improved in the control group. Now I'm going to randomly shuffle them. So you put them all in a big group, shuffle them out. And in this most recent shuffle, if dolphin therapy had nothing and you're truly just randomly shuffling them into each group, then group A got 5 successes and group B got 8 successes. You can see the dark ones are the ones that were originally up here in group A. Then you can kind of see how they move from group to group. And now it'll show you a new shuffle table. So here's the observed table. This is what I actually got in my study. My shuffle table is if I just randomly shuffle them. So here you had a proportion in one group of 0.33, the proportion in the other group of 0.533, and the shuffle difference in proportions is negative 0.2. So that is just one shuffle. If I click shuffle again, now, actually, it did the same thing. We got 5 and 8, and we got another shuffle difference of proportions of negative 0.2. Let's try again. Now, I got 6 in one group and 7 in one group. So now my difference in proportions is only negative 0.067. So let's come back to our notes. You can see I did this 3 times for your notes, so you can see 3 different attempts. Okay. So for my first attempt, I got a shuffle difference of negative 0.2, just like we actually did. Okay. The next time, I got 7 in one group and 6 in one group, and that gave me a shuffle difference of proportions of 0.067, and you can see that that's that one right there. And then the next time, I got a shuffle difference of proportions of 0.2. That's this one right here. Now, I just want to make sure that you're understanding where all of this is on the paper. So let's kind of double check some of our information. So when it says, what is the conditional proportion? So we're only looking at attempt 3. So this attempt right here, we're only going to look at this. What is the conditional proportion of people in the dolphin group that improved? Well, there were 8 people that improved out of 15. Oh, sorry, 8 out of 15, which gives me 0.533. And you can see it will just calculate it for you. And conditional people of proportion people in the control group that improved, there were 5 that improved out of 15. So 5 divided by 15 equals 0.333. And what is the difference in the conditional proportions? You just do the 0.533 minus 0.333, which gives me 0.2. And that was our shuffle difference of proportions. Now, an interesting thing I want you to notice is the marginal totals are the row and column totals. When we do this, notice, look at all 3 of these attempts. What do you notice about the marginal totals? So like the 13, 17, 30, 15, 15, 30, 15, 15, 30, 13, 17, 13, 17, 30, 15, 15. They're always the same. That's not a coincidence. Okay, not super important to you now. Okay, but if you were to get into the theory, that would be important. Okay, so they are always the same. If you're trying something and they don't seem to be the same, you might need to go back and check your settings and see if you messed something up. So now we've done several attempts. So how did our shuffled differences in conditional proportions compare to our observed difference in conditional proportions? So our observed of our p hat for the dolphins minus p hat for our control was 0.467, right? So here was my observed right here, 0.467. My shuffled ones were like negative 0.2, 0.067, 0.2, so they seem to be smaller. Okay? Or my observed difference, so the observed seems to be bigger. Well, we've only done a few things right now. So I've only done it 3 times. So maybe if I do it a few more times, like maybe I'd get different results. Like maybe, let's see what happens if I try it 10 times. Okay. So at 10 times, now look, what do I get? So my shuffle differences in proportions go from like negative 0.2, maybe that's like 0.3 maybe. So you can actually click on it, it'll tell you that it was 0.33. Okay. Maybe we can shuffle a few more times. Okay. So now it looks like I'm going from about negative 0.33 up to 0.333. But most of the time I seem to be around 0. And if you look at the mean is pretty close to 0 at the moment. Okay. So what we want to do is we want to determine how often do we truly get a result at least as extreme as our actual study by just chance alone. So we need to repeat this random assignment process under the null hypothesis that dolphin therapy doesn't work many, many times. So we should do thousands of shuffles to see what values we typically get for the difference in conditional proportions when dolphin therapy doesn't work. So this is called the null distribution. Remember, that's the distribution of possible sample differences in conditional proportions if the null is true. So we go to our applet and we just ask it to do 10,000 shuffles now. Now, some of these data sets, if you get a bigger data set, this is the one of the applets that will actually slow down. So if you get a huge data set, and you might only have to be able to do like 1,000 shuffles before it slows down. But for this, it can still do it just fine. So now I've done 1,000 shuffles. And you'll notice I did get down to negative 0.467 once or twice, up to 0.467 occasionally, but not very often. It seems very rare. Really, we're right here, usually centered in the middle, around close to 0. Let's look and see what I got when I did it before. So I did 10,000 times. My mean, all of these different sample differences were around 0. You can see the standard deviation of all those different sample differences. And you can see it count. Okay. So I put in to count the samples greater than 0.467. That was our observed difference. Okay. And I counted and I got 0.0019. So that is my actual p-value. And it does seem to be very small. Let's look at what we have here. So it looks like the difference is usually centered around, it said 0.003. Okay, but if I did this many, many more times, I only did it 10,000 times. If I do it lots of times, it should theoretically be centered at 0. So theoretically at 0. Okay, but you're doing simulations, so it's not exact. So we can count the number of times we got a shuffle with the difference of 0.467 or more, which is what we put in here. So this is our p-value. So our p-value is 0.0019. This means that if dolphin therapy does not work, then there is a 0.0019 chance that we would see such a big difference in our groups. So under the assumption that dolphins do not make a difference, if we repeated the random assignment process many, many times, we would see results as extreme or more extreme than our 0.467 difference, about 0.0019 of the time. Not very big, right? That's a very small p-value. These are just two different ways that I could phrase it. Okay? They both mean the same thing. So is that statistically significant? Is it smaller than 5% or 0.05? So smaller than 0.05. So yes, so the p-value is smaller than 0.05. So it is statistically significant. So if I ask you, do you think it's plausible that dolphin therapy does not work and we saw such a big difference just by random chance of who was assigned to each group? Well, I mean, it's theoretically possible. It might happen like 0.1% of the time or 0.2% of the time, but it is definitely not plausible. So it is not plausible that dolphin therapy doesn't work, and we just saw this because of who we put in each group. So do you have evidence that dolphin therapy works? Well, 0.01, that's a very small p-value. Okay, and so I would say that we have very strong evidence that dolphin therapy works. Okay, let's see how we would do our official hypotheses. So we can think of the long run proportion of times that dolphin therapy improves depression as pi with dolphin written by it. Okay. So pi, remember that was our population proportion. So this is my population proportion for everyone in the dolphin group. Or you can think about it as a long run because it's for anyone that might have depression, not just like one set population. And the long run proportion of times that control therapy improves depression as pi control. But really, for our study, we weren't interested in looking at either of these individually. We want to compare them. So our official parameter, these are kind of like little individual parameters, but we want to look at our official parameter as the difference of population proportions. So we'll look at pi dolphin minus pi control. So the null hypothesis would be that dolphin therapy does not work. Okay. Or if you want to say dolphin therapy is not associated with improved depression levels. Remember, null hypothesis is always that status quo, nothing interesting happening. Now, if we were to think about it in terms of our population parameters, if dolphin therapy does not work, then shouldn't these population proportions be the same? Okay. And if they're the same, what happens when you subtract two things from each other when they're the same? Like if you do 3 minus 3, you get 0. So if these proportions are the same, they should subtract to 0. So we could say the difference in the proportion of all the patients with depression who improve with dolphin therapy and the proportion who improve without dolphin therapy is 0. Okay. So the null hypothesis will always be that it's equal to 0. The alternative hypothesis is that dolphin therapy does work, or that dolphin therapy is associated with improved depression levels. Okay. Or you can think about as the difference in the proportion of all the patients with depression who improve with dolphin therapy and the proportion who improve without dolphin therapy is what? Okay. So in symbols, if we subtract the two population proportions and the dolphin one is higher, so we want this one to be bigger, and we want the control one to be smaller if we want to show that dolphins work, then something bigger minus something smaller should be greater than 0. Now, someone might ask, what if we switched our groups in our calculations? So like suppose a coworker switched the groups. So they did everything that you did, but they switched the groups and they did control minus dolphins. Okay, so let's think about that then. What would be our new statistic? So now if I do the sample proportion of control minus the sample proportion for dolphins, if you remember this was 0.2 and for dolphins it was 0.667. Okay. So now if I subtract, I'm going to negative 467. If you think about that, that's very similar to what we had before. I just switched to a negative, right? But the number's the same. Let's see, what are our new hypotheses? So now I would do pi for my population proportion for control minus pi population proportion for dolphins. This one is supposed to be smaller. The dolphins are supposed to be bigger. And if we do a small number minus a big number, that should be less than 0. And let's put it in our simulation and see what happens with p-value. Okay, so here, this is my original of dolphin minus control. So dolphin minus control. And here, okay, listen. So that's my dolphin minus control. Notice right here it says dolphin minus control. And my observed difference in proportions is 0.467. And when it finds the p-value for me, I put in greater than 0.467. And I get a p-value of 0.0019. But on my applet, all I have to do is click this button right here. I just click the button, it will switch from control minus dolphin, and it will change my observed difference, and it will change everything else, but unfortunately you do have to shuffle again and count again. Okay. So I switched it, I reshuffled, but now remember, what are my alternative hypotheses? My alternative is that it is less than 0. So I actually need to put in a less than, and I put in my negative 0.467, But notice that my p-value is very similar. Now, if I was doing this theory-based, they'd be exactly the same, but because this is a simulation, they're not exactly the same. Okay. But the p-values are very similar, so let's write that up above. So it's almost the same. And if you did a theory-based, it would be exactly the same. Simulations just aren't as accurate as the theory-based, and that's why it's not exactly the same number. But your statistic will just change from a positive to a negative. Your p-values will come out the same, or at least pretty close. Your hypothesis will just switch to a less than versus greater than, but your final conclusion will always be exactly the same. So it doesn't matter which group you put first as long as you're consistent for the entire problem. So if you start off doing control minus dolphin, you have to do that for the entire problem. Okay, some official pieces here. The statistic is your difference in conditional proportions in your sample data. So we'll do that with our p-hats. And the parameter is the difference in conditional proportions in the population, or maybe it's long-run proportions. Okay. So this will be pi 1 minus pi 2, because those are your population proportions. The null hypothesis is always that there's no association, so it will always be pi 1 minus pi 2 equals 0. It'll always be an equals. Okay. And it'll always be equal to 0. The alternative is that there is an association, and it might be a less than 0, a greater than 0, or an equals than. Now, sometimes you'll see it written like this. So instead of doing pi 1 minus pi 2 is less than 0, you could rearrange this, pretend you're in an algebra class. If you add pi 2 to both sides, you'll have pi 1 is less than pi 2. Sometimes that's a little bit easier for us to think about, like, so the proportion for the dolphins, well, let's write out on the next one. So like this next one, we can say, or pi 1 is greater than pi 2. So that would be the same as saying, like, the proportion for my dolphins was greater than the proportion for my control. So that's the same as saying the proportion for my dolphins minus the proportion for my control is greater than 0. This is just more intuitive to people. This makes sense with the way we're trying to teach you to think about things. Okay, but you might see it written either way in the homework. And or it could just be a not equal to 0. So if they don't tell you which way they think this relationship should go, you should just say, is there a difference? Your standardized statistic, remember, standardized statistic has always been how many standard deviations our statistic is from the mean of the null distribution. So you just do your statistic minus the mean of the null distribution over SD of the null distribution. Now, when we compare to proportions, we're always saying, setting up our null to be equal to 0. Okay, and so the mean of the null distribution, this part will always be 0. Okay, and so you can think about as the z is how many standard deviations our statistic is from 0. Okay. So instead of saying the mean of the null on your interpretations, you'll just say how far it is from 0. The p-value is the chance of getting such a big difference in our sample proportions if the null is true. So same p-value as always, it's just what's the chance of getting our sample data or something more extreme if the null is true. And when we say the null is true in this situation, it means there's no difference in the population proportions, or the treatment does not work, or there's no association between the variables. Those are just different ways that you could phrase it in your interpretations. We can find confidence intervals just like we've been doing. So the confidence interval for the difference in population proportions, our formulas have been statistic plus or minus the margin of error, or our statistic plus or minus 2 times the standard deviation of statistic. So for proportions, when we compare two proportions, it will be what's the difference in your sample proportions plus or minus 2 times the standard error of that difference in your sample proportions. Now, this is a very complicated formula, the standard error of those differences. We're not going to make you do it at all. We'll just use the applet to find the standard error. And confidence intervals and significance tests, just like we did before, if 0 is in a confidence interval, then 0 is a plausible value for the difference in population proportions. So if 0 is plausible, that means the p-value would be big. That means we're not statistically significant. That means there's no evidence for the alternative. But if 0 is not in the confidence interval, then 0 is not a plausible value for the difference in population proportions. So the p-value would be small. That means you're statistically significant and you have evidence for the alternative. Now, all of these methods are going to work whether you have an experiment, which means the randomness comes from which people you put in each group. Okay. But sometimes we're taking samples from two different populations and finding the sample proportions in each one and comparing. That happens when we come from an observational study. And so then the randomness comes from which people we happen to get in the sample. All of these formulas work the same whether it came from the experiment or the observational study. Okay, and just remember the applets don't work if you put spaces in the variable names. So for the dolphin example, let's find the 95% confidence interval for the difference in population proportions. And recall that p hat for the dolphins minus p hat for the control equals 0.467. So we said it's supposed to be our statistic. So p hat for dolphins minus p hat for control. That's my statistic. Plus or minus 2 times the standard error of my statistic. So we'll do my sample difference of 0.467 plus or minus 2 times the standard error, which that's what you have right here. Okay. It says SD, but it's just the standard error, or what was the standard deviation of all those different proportions we got, or the differences in the proportions. And so we just do 2 times 0.183. So this is going to be 0.467 plus or minus 0.366. So we do 0.467 minus 0.366. We get 0.101 to 0.833. So what is my 95% confidence interval? It's 0.101 to 0.833. Now, you can do that by hand, and on the test, it will just show you this null distribution, so you kind of have to do it by hand on the test. So please do it by hand on the test. But on your homework, here's how you can double check. You can click for 95% confidence intervals for the difference. And, oops, sorry, I'm doing control myself. And so switch back. It says 0.154 to 0.78. Notice this is not exactly what we got. And that's to be expected because they're actually using the theory-based approach. Okay, and they're using some different fancier formulas that we're not going to teach you. Okay, so it's not going to be exact, but it will be kind of close just to kind of help you double check. But get used to doing it by hand because on the test, I will just give you this picture. It will say the mean in SD, and you have to do the confidence interval this way. Now, how could we phrase the interpretation of this confidence interval? There's a few different ways you'll see it written. Okay. Really, it just means we're 95% confident that the difference in our proportions is between those two numbers. Okay, but there's a lot of different ways to phrase that. So we can say something like, we're 95% confident the difference in our population proportions, okay, of people that improve is about 0.101 to 0.833 higher with the dolphin group than with the control group. That's really big, right? I mean, that's a big spread, so we're not like super sure what it is, right? But if you were told that the chance it was like 0.83 higher to improve with the dolphin group, I'd probably sign up to go swim with dolphins, right? Whereas if someone told you the chance to improve might only be like a difference of 0.1, you might not be so impressed. Or I say we're 95% confident the probability of improving depression is about 0.101 to 0.833 higher with the dolphin group than with the control group. Or maybe like we're 95% confident that the dolphin group increases the probability of improving depression by about 0.101 to 0.833 when compared with the control group. Either way, though, based on the confidence interval, what could you say about the p-value? Well, when you look at that interval, 0 is not in the interval. So we can say that the p-value has to be small. So 0 is not in the interval, so 0 is not plausible. And anytime 0 is not plausible, that means your p-value has to be less than 0.05. So what is your, well, 0.05 because it was a 95% confidence interval. So what is your conclusion? We say that we have evidence that dolphin therapy works. Because we're pretty sure that the difference in proportions is something bigger than 0. We might not know exactly what it is, but it's bigger than 0, whatever it is in there. Okay, so one more example. Are Americans becoming more or less likely to donate blood at least once per year? Notice I say like more or less likely is saying we don't really know which way our hypothesis should go. We're just going to kind of see is there a difference. To investigate this question, we can analyze data from the General Social Survey, which is a well-respected survey conducted every 2 years on a nationwide random sample of American adults. One question on the survey is whether or not Americans have donated blood in the previous 12 months. Below is a two-way table comparing responses from 2004 and 2014. Let's see, when we look at this, what would the units be? Okay. They're surveying people, or they're surveying adult Americans, so the units would be like the individual adults, okay, American adults. What do you think the explanatory variable would be? They're trying to see, like, did our rates of donating blood change, okay, over time? Okay. So we want to compare from 2004 to 2014 to see if we're changing how much we donate. So the explanatory variable is whether it is 2004 or 2014. So you can write, this is your explanatory variable, this is your response variable. In section 6.1, we said it doesn't matter which way you put the explanatory variable, if it's the columns or the rows. However, to use the applet, you do need your explanatory variable in the columns just to use the applet. Okay. And the response variable is whether or not they donate. So let's see, is this an experiment or observational study? Well, for it to be an experiment, the researchers have to control which group you're in. Obviously, the researchers couldn't control people and put some of them in 2004 and some people in 2014. So obviously, the researchers didn't control which group they were in. So it is an observational study. So is there random sampling? Okay, did it tell you that it was a random sample? I did say random sample, so we'd say yes. Okay. Is there random assignment? Did we randomly assign them to groups? Well, we didn't assign them to groups at all, so no, because we didn't even assign them to groups, let alone randomly assign them to groups. Let's find our conditional proportions. So the proportion of people in 2004 that donated it, that would be this 230 out of 1336. So 230 divided by 1336 gives me 0.202. And the proportion of people in 2014, that would be this 161 out of 1315. That gives me 0.122. So if I want to, now this would be, let's make sure we label. So this is my sample proportion for 2004, and this would be my sample proportion for 2014. So the difference in proportions, that would be my 0.202 minus 0.122. Now, if you decided to do the 0.122 first, if you want to do 2014 first, you could do that, but you'd have to keep the same order throughout the entire problem. I'm just going to do the 2004 first because that's what was written first in my table. Let's see. So what does that give me? 0.8? So 0.08. So what is my statistic? My p hat for 2004 minus my p hat for 2014 equals 0.08. That was my proportion, my difference in proportions for my sample. Okay. But what is the parameter? You could think of the population proportion of people in 2004 that donated as pi for 2004. And the proportion of people that donated in 2014 as pi of 2014, so that's for the entire population. So my parameter of interest would be my pi for 2004 minus my pi for 2014. I don't know what that is, that's why we're going to use statistics to try and maybe estimate it with a confidence interval. So the null hypothesis is always the dull status quo, nothing interesting, so it's always going to be that there is no difference between the proportion of all the people in the U.S. that donated between 2004 and 2014. So time and donation rates are not associated, and Americans and Americans were equally likely to donate blood in 2004 and 2014. So you could say that pi for 2004, population proportion, minus pi for 2014 equals 0, since they're the same, they should be equal. Or you could do pi for 2004 minus 2014 as, you could put that they are equal to each other. Those two population proportions are equal. You can write it either way. The alternative hypothesis is that there is a difference between the proportion of the people who donate between 2004 and 2014, or time donation rates are associated, or Americans were not equally likely to donate blood. And so you could write this as with the pi of 04 minus pi of 14 not equal to 0, because they didn't tell me whether we thought it was less or greater. We just want to know, did it change? Or you could write it as pi for 04 equals pi for 14. This one makes more sense to people. This one just helps us put it in, think about what our applet is doing. So let's find and interpret the standardized statistic. But to do that, we need our results. Okay, so we go to our applet and put everything in. So I'll do 2004, 2014. I'll say donate 230 people, 161. Not donate 1106, 1154. When you're done, double check all of these totals. Okay, so 391, 226, 2651, all of those totals look right. Click use table, don't forget that. Okay, use table, your success is donate. We want to look at the people that donate. I'm doing 2004 to minus 2014, that looks right. I can click show table. I can see my conditional proportions. I must have hit something in my calculator wrong earlier. So I do apologize. If you go back up on your notes, 230 divided by 1336 is 0.172. I'm not quite sure how I got 0.202. So that's going to change a few of our results. 0.172 minus 0.122 should give me 0.05. I apologize for that. Again, I'm not quite sure what I put in my calculator. So when you look at it, you can see my proportion for 2004 is 0.172, my proportion for 2014 is 0.122, and my difference in proportions that I actually observed is 0.05. Okay. Now, when it says find and interpret the standardized statistic, to do that, I actually need to go through and shuffle everything. So I'm going to do, this is one of those times where 10,000 shuffles is going to take a really long time. So I did it for our notes, but here I'll only do 1,000 shuffles to show you. You can see that it will give me my mean and my standard deviation. And I can also, for my p-value, I can come through and count my samples, but I don't need that yet for my standardized statistics. So let's just find our standardized statistic. Z is equal to our statistic minus the mean of the null over SD of the null. So in our case, our statistic is what we actually observed as a difference, so 0.05, minus, what was the mean of the null? Here, notice it was actually 0, and theoretically it should be 0. So I can always just do 0, because I know it should be 0, whether or not the simulation is exactly 0, and divide by the standard deviation of 0.014. And that should give me should give me 3.57. Now, practice doing these by hand, because you never know when we'll just give you the null distribution. But I do want to show you, we haven't learned how to do the theory-based approach yet, but you could click overlay normal distribution. And, okay, I haven't actually put it in yet. But we're going to want to count samples. So remember, our alternative was a not equal to, okay? So not equal to, we're going to use what's called beyond here. So it means count greater than and less than, both of them. So we're going to do beyond 0.05. And so it will give me my p-value, but it'll also tell me here's my theory-based p-value and here's my standardized statistic of 3.63. Now this is my theory-based approach. That's always going to be a little bit different than my simulated approach, but you can see we got 3.57. They got 3.63 when you use the theory-based approach. It's just a way to double check yourself. Still do it by hand, but you can always come and double check yourself. Okay. On the test though, they might only give you this and you won't have the data, so make sure you still know how to do it by hand. So now, oh, let's see, we're supposed to interpret it. So we would say something like, our difference in proportions is 3.57 standard deviations from 0. Okay. And anything that's more than 2 standard deviations away is surprising. Okay, so this would be a situation where you're like, oh, that's surprising. So 0 is not a plausible value. We have evidence for the alternative. Anytime our z is bigger than 2, that means we have evidence for our alternative, because that would be surprising. Now let's find and interpret our simulated p-value. So let's see, this was our standard deviation. We counted samples beyond our statistic of 0.05. And looks like my p-value is 0.0002. So our p-value is 0.0002 because we just count anything that was beyond that 0.05 that we had as our observed difference. If we were going to interpret this, we would say something. If dolphin therapy does not work, then there's a 0.02% chance to get such a large difference in our sample proportions just due to who we assigned to each group. That seems very small. That seems very unlikely. Oh, sorry, I wrote dolphin therapy does not work. Okay. I was still in that mindset. So we're saying if the rates in 2004 and 2014 are the same, so that was our null hypothesis, then you only have about a 0.02% chance to get such a large difference in our sample proportions just due to, so in this one we're not assigning people to groups, they didn't assign people to groups, just due to who we randomly picked to be in our sample, since that's your source of randomness. I do apologize. If you noticed in the video, I'd accidentally switched the groups. So I have now switched on your notes. So the groups are still the same with 2004 first. So our observed difference was positive 0.05, and we counted samples beyond 0.05. Okay. So are our results statistically significant? Yes, because we have a small p-value. Did I say something wrong? Now, for this class, I'm only going to show you how to do all of this for the difference in proportions. Okay. However, you could also do all of these tests with relative risk. So remember right here where we have statistic, difference in proportions, I could actually click relative risk instead. Okay. And it will tell you what your observed relative risk is. So in like 2004, people were 1.4 times more likely to donate than in 2014. So that's just right here, my observed relative risk, 1.4. Okay, so we're more likely to donate in 2004. Now, if you think about this, if our null hypothesis was true, that the proportions were the same, shouldn't that be 1? So we could actually do a test to see how close my shuffled relative risks are to the number 1. Okay. And so you can come through and you could shuffle. And every time, instead of finding the observed differences between your proportions, it will show you the relative risk. Okay. So like this time when I did it, my proportions were pretty close. So my relative risk was pretty close to 1. And you can see when you look at the 1,000 different relative risks that they are all centered around 1. Okay. And you could go in and you could count samples beyond what you got, which was the 1.406. And you can count beyond, so it does it on both sides. Okay, and it will tell you this time my p-value was even closer to 0. It stopped rounding at 0. Or stopped rounding at 4 decimal places and just gave us 0. Okay, so looking at this, you could find a p-value, you could find a statistic. We're not going to teach you how to do both, but everything we did with the difference in proportions, you could do with relative risk.